Then there is another one, displacement length ratio. So there is no speed. This is for volume or weight. So that shows another way of fatness or fullness comparing to slimness when predicting speed and power. But that is also used in old days to predict, because as a designer, you need to predict speed and power many times to guarantee the requirement coming from owner, the guest, customer. But you don't know until you cannot sure until the ship is really built and also running. So prediction is very important in old days. That's why they develop many different technologies to make a prediction. But this is the same as nowadays. As a designer, you need to know how to predict the performance when you design something, product. So displacement length ratio is defined by this number, the triangle divided by length and triple power, but the unit is different in long tons and feet. So if you see the remember the block definition of block coefficient, it looks similar, right? But different. So volume, but that is displacement is weight. Long ton is weight, not volume. And they use the length 3 times multiplied instead of LBT multiplied. So that unit-wise is almost same, but a little bit different. So in old days, before CB is developed, so CB is a non-dimensional number, but displacement length ratio is not non-dimensional, but dimensional. But anyway, they use in old days for as a designer. And at the table, you see that CB and speed length ratio and displacement length ratio. 3 numbers of typical oceanographic research vessel, power yacht, and Great Lake bulk carrier. But they are very special ships, not big ships in nowadays. Anyway, so the CB is a little bit going up because this is probably big ship, cargo big ships. Smallest one is yacht. And speed length ratio, this is lowest. And this is highest because this is a power yacht. Right? No, sorry. This is highest. Sorry. Speed is high. Ocean lowest is this one. I should write down the arrows. And then the displacement length ratio is also higher here. So those same ranges. So this ship is very special in that length is long, and speed is very low. So there is a typical, very special. But you need to have another column for typical oil tanker bulk carrier. That shows you different ones. And hull form coefficient and hydrostatic curves. So another thing you need to, as a designer, to know is how much cargo can be carried and what can be the buoyancy of the ship. Then you need to calculate underwater body volume. As you remember that all the definitions of coefficient, you need to have a volume of the ship, underwater volume of the ship, right? Volume of the displaced water. Then, but the shape of the ship is very curved way. We call the free-form surface, so that the volume calculation is not easy. Right? So they use different, in old days, nowadays a computer is doing such a calculation, but in old days, you need to have a hand calculation. So that this one is Bungian sectional area curves. And each section, each station, section or station, they calculate area by using this kind of, this is a sectional shape of the hull, skin shape at some position of the length. This one is another position of so this is the shape of the hull. And then you can, and then water line, the draft line, let me say water line 2. Water line 2 can be for this ship is design shape, draft line. Then area can be calculated by dividing into very many strips, and then curve can be approximated by straight lines with a thin, narrow strips, and then you can approximate the area of this section. So each section you draw this kind of curve as depending on the draft line, the submergence, the water line, you can calculate area, right? Area water line 1, 0.5, 1.5, and 2, and 3, and 4. So below the curve water line, you can calculate the area. Then you can create, draw this kind of curves for each station. So here it is the how can I say? The linear dimension is the area, and that yellow area is showing your volume. Okay? So you calculate area here, but that one is drawn here as dimension, length. And again, this sectional area of yellow color then gives you the volume. But anyway, in this way, you can draw this kind of curve. This we call the sectional area curve. And this curve shows area dimension. This dimension, vertical dimension, is area, sectional area at specific position along the length. This is the length of the ship. And this dimension, the vertical dimension, let me say as a Z or G, shows your area of that section at that position. And by integrating or calculating the area under this curve, you can calculate the volume of the ship. That's how the volume is calculated in old days, using Bungian sectional area curves. In old days. But then it comes with a computer, and computer replaced this Bungian sectional area calculation. And then nowadays, more higher level of calculation method is developed. So we don't know how computer is doing, but basically the idea is the same. We do not know. So area is integration, right? Integral. Mean section coefficient again, same as area, midship, and breadth at the waterline and draft. CP again. So CP and CB is related with its numbers. CB and CM can calculate the CP. Question? No question. So heliostatic curves gives you fullness of the ship, the coefficient calculated, and also the most important thing is the volume of the ship can calculate by the section area. So this is tough work in old days for naval architecture. And LCV, longitudinal center of buoyancy, because the ship displaces water, so that the volume, submerged volume of the ship has a volume, and there should be a center of the volume, right? We call this the center of the volume or center of the buoyancy. If you do not speak, you can turn off your microphone, please. Otherwise, we can share the noise coming. So LCB, so center of buoyancy is the same as center of volume, but that volume is submerged volume. Right? And longitudinal center, so center of volume is a position in the space. So there's X, Y, Z position, right? And X means you can say this is a longitudinal dimension. B is a breadth-wise dimension, and Z can be the vertical dimension. So X, it can be the same as LCB, longitudinal center of buoyancy. The XYZ coordinate value of the CB. Right? And forebody and afterbody is two sections of this ship. At the bottom, you see that. And this is the front part, forebody of the ship, and afterbody of the ship. And forebody is usually more slender than afterbody because of the wave distraction. Wave is coming from the front, and also the engine is located in the back, so that afterbody is usually full. And forebody is related with or depend on affecting wave making resistance, wave pattern, braking resistance, and sea keeping. Once again, how well behave along the rough sea is sea keeping. Afterbody, resistance, propulsion, because propeller is here, so the shape of the afterbody is affecting the performance of the propeller. And wake distribution, cavitation, maneuverability. Maneuverability is maneuvering. How can I say? When you drive your car, you can want to turn fast, right? In a curved way or in a corner. We call this is a maneuverability. How well we can operate along the pathway. Right? Drive test usually have a test such as passing through the special corners and S-shaped course. And engine arrangement is also afterbody. And the picture here, you see that LCF and LCB curves of the ship. This is depending on the water line, submergence, how the water is here or what water is here up to the draft line, so that the center of buoyancy is changing. So in low draft line, center of buoyancy is at front, more front, but coming backward because this area is full. Comparing to this is slender. And right-hand side is also LCB. But for the and fruit number is shown, optimum LCB is shown here, and block coefficient. So that as a designer, you can use such a graph to determine your optimal LCB as a reference for your design. Question? No, center of volume, center of buoyancy, same. Volume or buoyancy. And there is a vertical center of buoyancy, longitudinal center of buoyancy. And this is a midsection mark, symbol. LCF is the longitudinal center of flotation. This is not volume, it's area center. This is a volume center. Area center, and then weight. LCF is important for position, where you can add a weight, small weight, without changing the trim. If you remember riding a small boat yourself, how many of you had a chance to ride a small boat yourself? Can you raise your hand, please? How many of you, again, how many of you had the chance to ride a small boat? Okay, Gihan does not have a chance, all right. But if you have a chance to ride a small boat, you need to careful about position of yourself. You cannot run around the boat if you are not mind, then the ship can be capsized or trimming, right? Depending on your position of, because your weight, right? And then it is saying that the center of flotation, the area center. Then if I loading a small 1 kilogram or 10 kilogram of weight at the LCF, then there is no trimming. Trimming is an angling of the ship because this is center. Right? That is the meaning of this one. So as a designer, at the late stage of ship design, you need you have a request, special request from the customer that he wants to put a special device onto the ship. Then this additional device can create unbalance of the weight and buoyancy, so that the trimming can be the problem. So in that case, you may think about this using LCF numbers. But this is a special case, right? And let me go on to, video. Short video. I hope. Oh, it's a long one. I will cut off at This is naval engineering, means Navy.
Hello, my name is Laura Alford. This is the first lecture in our series on hydrostatics, and it is on the geometry of ships. So ships, like all specialized things, they have their own set of terminology that might be unfamiliar to you if you have not run into it before. So that's what this lecture is sort of aimed at familiarizing you with. So the first thing, and the major thing, is the hull. The hull is the big outside part of the ship that you see if you go see a ship down at a dock. The front part is called the bow, and the back part is called the stern. Left is port, and right is starboard. If you are standing in the middle of the hull and you're walking towards the bow, you're said to be going forward. And if you are in the middle of the ship and you are heading back towards the stern, you're said to be walking aft. Now you can see from this is just an example hull here, and this little kind of there's a bulbous bow. That's that little part that sticks out. This is very complicated, right? It's very curvy, it's higher in some parts than others, it's narrower in some parts than others. This is pretty complicated. And it gets kind of tricky talking about the hull if you've got a problem and you're trying to explain to somebody where exactly it is or what's going on. So we've got some reference planes that we can use to help ourselves with. So there's a big vertical one that goes down the center line of the ship. It is very creatively called the centerline plane. There's a horizontal plane called the waterline plane and a transverse plane that's called the midship plane. You'll notice this little symbol here with the circle with the two arcs bisecting it, sort of. That's the symbol for the midship. That's the middle of the ship. So if you see that symbol, we'll run into that before, but that's all it means. It's just put at the center of the ship. Right. As an example, take water lines. If you were to take the waterline plane, make a bunch of different copies of it, and run it from the keel line, which is the bottom of the hull here, all the way up to the top deck, you get these blue lines here. And from the side and from the front, they look straight, right? Because they are horizontal slices of the hull. But if you look at this from the top or from the side, sort of from this oblique view, then you get a sense for the curvature of the ship as it changes from the keel all the way up to the top decks. And so now we say, okay, here's some lines. We can start to see more of how the hull is changing, what its real shape is here. Similarly, if you take the midship section plane and you take a bunch of copies of it and put a bunch forward and a bunch aft, you get what are called stations. The stations here from the side and from the top look straight, which is good. That's what you want. And then from the front or the back or from this oblique view, now you get these sectional curves here. And you can see that they illustrate how the hull is changing as you go from the bow to the stern. Here, you can see down below here, like if you were to plot all those red lines on top of each other, it would get kind of busy, be tough to see which ones are going where. So generally we put the stations that are forward of midships on the right hand side and stations that are aft of midships on the left hand side. This way you can see how things are changing easier. And most ships, almost all of them, have a port starboard symmetry. So you're still retaining all of the information here. Okay. So finally, if you take the centerline plane and you take a bunch of copies and you send them port and starboard, you get what are called buttock lines. So again, from the top and from the front or back view, you get straight lines. But then if you look at it from the side or from this oblique view, now you start to get these contours as you go from port to starboard or left to right. So now you can see how is the ship's hull changing from side to side. And you can look at these lines, and they're sort of like the lines of pressure on a weather map, right? The closer the lines are on a weather map, then the higher the wind is going to be. Similarly, the closer the lines are on these slices here, the closer the lines are, the more curvature there is, and the farther apart they are, the less curvature there is. You can take all of these lines, put them all together in something called a lines drawing. The profile view at the top shows the buttock lines, the plan view shows the water lines, and then the body plan shows the stations. Again, remembering that the body plan shows the stations that are forward of midships on the right and the stations that are aft of midships on the left. Now, in general, a lines drawing is going to have a whole bunch more information than just what I've shown here. They'll have station numbers and dimensions, scales, labels, all this stuff. This is just an illustrative example here, just to show you where these lines are coming from. Okay, so there are several different lengths that we end up using when we talk about ships. There's an overall length, which is very important when you're looking at how much dock length do I need to actually bring my ship up to a dock, right? You got to make sure you have room enough for the entire ship. But when you're looking at this ship in a horizontal slice, and if you do the same thing, but now you do it on the waterline, you get the length on the waterline. So you can see an example here of what that means in terms of some of the slices of the hull that we've already seen. There are two major vertical measures here of the ship. One is depth, and that's the overall height of the entire hull. But when you go back and you're looking at buoyancy, stability, sea keeping, you want to actually, your commonly used ratios are length to beam, length to depth, beam to draft, and beam to depth. So again, just know these, remember what they are. They're the hull. This is the part that's in gray. Now, if you do the same thing, but you do it right at the waterline where the hull intersects the surface of the water, you get the area of the water plane, this A sub W. Flotation. The center flotation corresponds with the trim axis, again, which is what the ship is going to rotate about. The center flotation is a point, right? So it's got three different coordinates to it. There's longitudinal, transverse, and a vertical. Because we use V later on for velocity, we had to come up with something different to talk about volume, and so this is what we use this triangle for. You may have seen it with as a gradient symbol in math class, but here we use it as the volume of water that's displaced by the ship. So it's that part shown in red. So you can see that it's not the entire volume of the hull; it's just the part that is underneath the water. Okay. The center of this volume is the center of buoyancy. It is the point through which the total buoyancy acts. So again, it's a point, so it has three dimensions. So again, it's not going to be the total area of the hull. It's just what corresponds to being underneath the water. Similarly, if you do this at midships, then you get the midship station area. And the same thing is just the area below the design water line at midships. Now, if you do that all along for all of your stations, you can plot the sectional areas on the sectional area curve, and you can see that it has less area at the bow, and then it increases as you get towards midships, and then it comes back down, and you have less area at the stern. Because the area would then be related to the volume, this kind of gives you an idea of where your buoyancy is going to be coming from, which we'll talk about later. So the bulk of buoyancy is going to be coming around midships, not so much at bow and stern. Your hydrostatics program will calculate this for you. You can do it for a lot of different drafts. You can compare different ships, even if they're the same kind of ship, you can compare them using the Bloch coefficient. So it describes the overall fullness of the hull. And you can see here, so it's the total volume that it could possibly take up based Similarly, you have a prismatic coefficient. Because the midship sections of ships are so full, sometimes they can overwhelm the differences between the bows and sterns of different ships. So here's one way that you can more directly compare how the bows and the sterns of different ships are. So in this case, you take the area of the midship, you extrude it out you don't get much of a change as compared to the block coefficient, but the destroyer, you do get a change. So midship section coefficient, again, you can sort of compare how full is a ship.
Okay, that's enough for today. So that's it. All right. Questions? No question? Then we can have a break. While we have a break, we can use TA and fix up the time. Right? Oh, there is another new survey.